Welcome to episode 12, Flight of the Soccer Ball. To model soccer ball flight, we will separately figure vertical motion, that includes gravity, and horizontal motion, that doesn't include gravity. We introduce two model tools that are new to us. One is an XY scope viewer. It will allow us to see the profile of the flight of the ball, without having to look at horizontal and vertical motion graphs separately and imagine their combination. The second is an if-then statement block system. It will be needed for switching the sign of vertical air resistance force after the kicked ball reaches the top of its vertical motion. Before the crest, air resistance fights the ball rising and acts with gravity. After the crest, air resistance fights the ball falling and acts against gravity. Since the whole flight is done near Earth's surface, we will not need to look up air density at high altitude. Air density will be a constant. For a soccer ball shape and size air resistance factor, we will follow the same procedure we used with Skydiver. Off the net we have a typical soccer ball mass of 425 grams. They also list a terminal velocity of 14 meters per second. First, we need newtons of attraction of the ball to the Earth. We have 0.425 kilograms times 9.8 meters per second. That gives us 4.16 newtons. Terminal velocity air resistance support also has to be 4.16 newtons. So to get our shape and size factor for the model, we have to divide 4.16 by our terminal velocity squared, 196. Therefore x has to be 0.021. Here are the velocity squaring blocks. The top one for horizontal and the bottom one for vertical motion. Here are our ball shape and size factors. To get air resistance deceleration to feed into our velocity, displacement systems, we must take whatever forces we have in newtons, including gravity if applicable, and apply them to the known mass of the ball, 0.425 kilograms. That is handled in these areas. For the horizontal model, all we have to do is divide air resistance newtons by ball mass to get acceleration, actually deceleration, ready to apply to my horizontal velocity account. For the vertical model where we include gravity, the newtons of gravitational pull will always have the same sign. Upward flight air resistance newtons will add to gravity before we throw our conditional branch switch at the top of the arc. On the way down, air resistance newtons will be subtracted from gravity newtons. Finally, net vertical newtons will be applied to mass, resulting in vertical acceleration. What should be the scope of this kind of simulation? The kick takes place on a millisecond time scale. The flight takes place on a second's time scale. We won't try to mix the kick with the flight. Mixing very different time constants doesn't work well. The result of a sharp kick is just initial velocities, and we will use those. If we want an initial slant velocity of 20 meters per second at a takeoff angle of about 45 degrees, we simply put 0.707 of 20 into each account for the kick. As the model runs, velocity will bleed down because of air resistance. The model is done when the ball touches the ground. After that, the model may report values, but we are not concerned with them. We will also omit modeling the bounce for the same reason we are not trying to model the kick. There are lots of bounce simulation demos on the net if the student is interested. Let's run our model first with air resistance turned off. Up in the horizontal section, we just turn off any modification of velocity. Down in the vertical section, we turn off air resistance and leave gravity on. Starting displacement is 0 for both x and y. To orient ourselves, we look first at graph 3 to find out when the ball lands. Graph 3 is the vertical part of the flight plotted over time, and when the vertical travel of the ball returns to 0, the model is over. We land at 2.88 or so seconds. Graph 1 shows that the ball never experiences anything but minus 9.8 meters per second squared. Let's construct a line up from 2.88 seconds. Looking at graph 2 with the line, we see that we end the model with exactly the same vertical velocity as we started, but with the opposite sign. No energy left the vertical part of the model. The bottom graph, vertical height as a function of time, shows that our ball reached around 10 meters high. Page 2 of the graphs. We draw our end of model time line again. Graph 3, our downrange progress shows that we landed about 40 meters downrange. Page 3 of the graphs. This is our new XY view, showing a perfect parabola. The ball reached around 10 meters high. Now let's turn air resistance on. Page 1. Graph 3. We see that we are now around 7 meters maximum altitude. We also don't spend as long in the air. Looks like 2.32 seconds. This is where we draw our vertical line for end of model time. The top graph is vertical acceleration deceleration, and it appears to wander all over the place. It starts at around minus 20 meters per second squared because significant air resistance is being added to gravity. Let's draw another line that corresponds roughly to the peak of flight. We look back at acceleration, the top graph. It is experiencing a flat patch at this moment. What is the value of acceleration here? 9.8 meters per second squared, because for the moment there is no vertical velocity and thus no air resistance. Look at our peak flight timeline versus the second trace. It confirms that the velocity at the peak is 0. Page 2. We draw our end of model timeline again. This is the horizontal motion page, and this motion experiences its greatest deceleration right after the kick, as the velocity squared will never be higher. Horizontal deceleration at end of flight is about minus 1.7 meters per second squared. What is our velocity at end of flight? We look at the value of the middle graph at the end of model time, around 5.5 meters per second, not the 14 we started with. Graph 3 is horizontal displacement. At end of model time, we are around 19 meters downrange, not 40. Page 3. What happened to our beautiful parabola of flight? Pesky air resistance scrunched it on the far end. Playing sports on Earth is not ideal. Our next episode is about the accounts and sine waves. Is circular motion the only way to approach sine wave? Maybe our solver with its account system has something interesting to add. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.